We're going to talk about transforming exponential functions. So here's kind of like our theoretical model or parent function for an exponential function, and we're going to talk about there's a whole lot of letters here with no numbers, so we'll try to see what we're getting at. And this is kind of a trick to help us with stretching and compressing. Okay, now the a value is usually known as the initial value within an exponential function. Okay, they usually call it initial. It also, because our b is our exponential growth or decay, it's also going to vertically stretch or compress. Okay, so when a is greater than 1, it's going to vertically, so let me just use v for vertically, okay? Vertically stretch. When a is between 1 and greater than 0, it is going to vertically compress. Okay, and one way you can do that is if you can draw the original function, you take each of the major y coordinates and you multiply them by your a value. So if it's less than 1, it's going to shrink their values. If it's greater than 1 when you multiply, it's going to increase all of their values, making it a vertical stretch or compression. Okay, b is your growth or decay rate. So a lot of times in this, first of all, for this to work, b cannot be equal to 1 because when b's value of 1, no matter what the exponent is, it doesn't work. B needs to be greater than 0 for us, okay? And when b is greater than 1, it's growth. And when b is between 1 but greater than 0, we're talking about a decay, okay? When you have like a fraction or something. Talked about v. And then just to stay on the vertical stuff, c has to do with vertical movements. So when c is greater than 1, sorry, not 1, greater than 0, we vertically move it up. And when c is less than 0, we vertically move it down, the entire function, okay? And then we'll keep going from there. What color? Purple. Okay, k is very similar to a. Okay, the only difference is k, when greater than 1, is a horizontal compression. So it's kind of the opposite of what the vertical stretch is. And when k is less than 1 and greater than 0, it's a horizontal stretch. Okay, and leaves us finally, what color haven't I used here? Black, I guess. Okay, D. D is very similar to C. It's just because if it's a negative in this equation, it's a little kind of like the opposite of what we had before. So D, when greater than 0, is a horizontal movement. And because this is a positive value, it's to the left. And when D is less than 0 or a negative value, it's a horizontal movement to the right. Okay? So there's a whole lot of rules there with these. So let's actually get into an exponential function for us. Let me see if I can get a quick graph going here. Scale 1. Scale 1 is going to run out really quickly for us. Maybe we'll go to scale 2 for this one. Let's see if that'll help a bit for what we got to do. Okay. Yeah, okay. So we're going to take actually, well, I guess we'll use an original growth model. So an original growth model, let's say we have y is equal to, and usually it's written as a is our initial value, b is our growth or decay, and x is the exponent. This is like the original of the function. In this case, we'll have b, since it's a growth rate, b will be greater than 1, so a simple value of 2. Okay, so it's 2 to the power of x, and I do want a different value for a, so let's just work with this. In this case, a is just a value of 1. Okay, so when a is 1, it doesn't do anything, and that should not look like a 12. Okay, so let's just graph what the original of this looks like. Okay, now one way to do that, if you're not familiar with them, is you can make a quick table, an XY chart, right? And you know, we have values all the way over here, and these are by 2s. I'm just going to go with that, start at -2, not -0, 0, 2, and 4. We'll use these values for x. So and the easiest one to do is when x is 0, so y to the power of, 2 to the power of 0 is 1. So when x is 0, y is 1, which is roughly there. Okay. When x is 2, Well, 2 to the power of 2, that's 2 times 2, that's going to give us 4. So when we're at 2, we're at 4 here. And when it's to the power of 4, I think it's going to give us 16. That's right. Power of 4 is going to 16. Anything outside of that would be too high. Which takes us to negative 2. Well, negative 2 is very similar to 2. It's just a fraction. So it's a quarter. Well, a quarter is something very hard to do here. And we know exponential functions have a horizontal asymptote across the x-axis, so it'll never quite touch this. So we have an original function that looks like this, okay? And it kind of goes out from there. So it is a growth model. Okay? What we're going to do is we're going to give values. I know I have a very big graph here, but our original was 2 to the power of x. So I'm going to give values and get you to choose what each of these values are. So, and I won't put them in their color, so I'll get you to do this here. Let's say this is 3, 2, too far here, 4x plus 1, then minus 4. Okay, so from the original one we had drawn, which is y is equal to a b to the power of k x minus d plus c. What are all the values? Which ones are a? Which ones are b, k, d, and c?
3 is a.
Okay, so 3 is our a.
2 is b.
Yeah, and we already knew that was our growth rate. Yeah.
4 is the k.
That's right.
D is negative 1.
Yeah, that's right. It's a negative value. Very good.
And C is negative 4.
Great. Good. So, okay, so we got them all. So what we're going to do is we're going to try to take these and apply all their movements. And maybe we have to go one at a time, right? A lot of times I find doing the stretches and compressions from the original values the easiest, all right? And that way, I'm going to take all these major points we've drawn. So we have some major points here. This one's at 2 1/4, right? This one's at 0 and 1. This is at 2 and 2. This one's at 4 and 16. So here are some major points we can play with. And recall, I gave us something that looked like this. We can take x and divide it by the k value, right? And we can take the y value and multiply it by the a value, right? So our a value in this one was what? 3. So our a value was 3. So we're taking all of our major y values and multiplying them by 3, okay? And we're also going to take all our major x values and divide them by our value of k, which happened to be, whoops, what did it happen to be in this case? 4. Okay, so we're going to divide by 4. So this will be kind of our model for our stretches and our compressions, right? So let's take a look at all these values. The first one is our y value of 1/4, okay? When I multiply 1/4 by 3, what do I get?
3/4.
Yeah, so this one's going to be 3/4. And our x value, we're going to divide it by 4. So we had, sorry, it wasn't 2, it was negative 2. What is negative 2 divided by 4 going to give us?
Negative 1/2.
That's right, so we have negative 1/2. So the new point, or this new point here, is really going to be at 1/2, and I guess we'll do this one in purple. Negative 1/2 and 3/4, so it's a little higher up. It's been compressed from before, right? It's been pushed in, and it's been vertically stretched, so it's been pulled up. Okay, let's do the same with our 0 here. When we divide 0 by 4, what do we going to get?
0.
That's right. That's going to be 0. And what is our initial value now going to be? We had 1 before. We have to multiply by 3. That's right. So the 0 stays at the same point, but we're going to be at 3 here. Our next one, we have a value of 2. So what happens to the 2 when we divide it by 4?
1/2.
So positive 1/2. And our y value, when we multiply this by 3?
6.
That's right, 6. So our next point is at 1/2, which is actually really close in here, and up at 6. Okay, and I know I did those in two different colors. Let's do them in purple here. Okay, and then our next value, finally, 4 divided by 4?
1.
That's right, so that's going to give us a value of 1. And our y value, when we multiply by 3, is Gonna be way off there, right?
Yeah.
1848?
Yeah.
Not even come on the chart. So, essentially what it's saying, though, is we have something that is far steeper. Okay, so it's taking off like that, and it's been compressed from before.
Mm-hmm.
So we did a lot there with that. And those are the vertical and horizontal stretches and compressions. But we still have to do our horizontal movement and vertical movement. So now we take those values, and this purple value here, and because of these points, it is a little tough. Our D was +1, right? Mm-hmm. Which means now all of our X values, we kind of subtract them by 1. We're going to move the whole thing back 1. So this point, this purple point here now goes back 1, so it's now at, what was it before, a half?
Mm-hmm.
Yeah. Is that a half? So we go back 1, so it's 1.5, which is really tight in here. 1.5. Our 0 goes to 1. Our half goes to -0.5. Mm-hmm. And our 1 in 48 is, now at 0. Yeah. So here's it's really tough to see again. That's the horizontal movement. And then the vertical movement, so we'll do our final one in green here. Everything goes down 4. So all of our y coordinates get shifted down 4. So when we shift this down 4, it's actually going to be 3.25, I think. So this one's be at -3.25, which means it's in there. This guy here, I should have wrote these points down. Well, the idea is we're going to shift it down 3. So I'm just going to try to draw it as best we can. I know this one's up at -0.5, right? So that's going to be 2.5, I think, something like that. Oh, geez. Looking a little ugly. But the idea is that it's moved down 4. And the best way to kind of go from there, from that is make sure we write all of our points down as we make the movements. But do each of those movements kind of make sense as we're going through? The last one was really messy, but it is a simple one. It's just taking each of those coordinates and moving it down 4.